Alright, let's talk about how to find all possible sequences of edit operations that realize an optimal cost. So before I was only storing one arrow, but if I look at all of the arrows here, I can see that there are certain cells that have more than one arrow coming out of it, which means that there's more than one possible move that you can do that will attain the optimal cost at that cell for matching a particular substring of the first one to a particular substring of the other one. And another thing you notice is that regardless of what cell you started, all sequence of arrows will eventually lead to the upper left. So what this means is all we need are the arrows, and we can get this. We just start in the lower right and we follow the arrows, keep following them until we get to the upper left. Now what's different now is we're going to store more than one arrow at each cell so that we can do this branching. So I'm just going to modify what I'm storing at each cell to, instead of being a single number, it's going to be a list. And also notice the bug here, by the way. So I know for all the elements of the top row I need to move to the left. That's the only place I can go. I forgot to fill in the last one here, and I forgot to fill in the last one down here. Okay. So same thing for the first column. I can only move up. I'm matching to the empty string at this point. I've got no characters left in here. So those are important base cases in the table. Alright, but anyway, so my intention is to actually store a list of elements. So I'm actually creating a 3D array here. My first two indices are the row and column, and then my third index indexes the possible moves that I can make, which isn't always the same number. So it's actually possible to have all three. I don't have it in this example, but it's possible that all three moves will tie. Okay, and so I know I mix up this notation sometimes, by the way. Just stick with the notation that you know from Java and C++ for 2D arrays. This will always work. I was trained in MATLAB to deal with a lot of this stuff. And that's notation that's a holdover from MATLAB. MATLAB is a predecessor to NumPy. But that only works for NumPy arrays, so just stick to this syntax. Okay, but anyway, so I want to store at every index of moves, at every row and column index, not just a single move, but a list of all moves that attain the optimal cost. So what I got to do is check. I say, okay, did the first move attain the optimal cost? If it did, then I will add 1 to the moves. Okay, and it'll do similar things for the other two costs. So I'll say if cost 2 attains it, add 2. If cost 3 attains it, add 3. So this will now add all the possible moves that I can make to my list of moves at each cell. Okay, so that has all the information I need. Great. I'm always a fan of incremental development. So whenever I do something like this, I'm going to test it right away before I do anything else. I'm probably not going to use this code anymore. I mean, I might be able to repurpose it a little later, but let me ignore it for now and just focus on. I'll just focus on, because I know I can do this translation step. Let me just focus on reporting the locations that I visit as I'm tracing. Okay. So let's just focus on that. So let me print out the moves. I think I'm going to need to format this, but let's look. So if I run this, okay, yeah, it's a little hard to see. Let me actually, so I'm showing you some debugging ideas. So now I'm going to write some code to output things in a way that's easy for me to bug. Let's say for I in range n+1, for j in range n+1, I'll print the moves at I, j. Just put a little space in between them. This isn't going to be perfect, but it'll be a little easy to look at. Okay, so what I can see is, let's see, the last row here. Okay, yeah, sure. So this one goes left, this one goes diagonal, this one goes up, this one goes up. There are two options here, either diagonal, which is a 3, or an up, which is a 2. That looks right. And the next row down, it's a 1 or a 3, so I can either go left or I can go diagonal. Okay, this is looking good. Okay, so now I'm pretty confident that this moves array holds all of the arrows, not just a single one. What I'm going to do now is actually make a helper method to trace all the paths. So I'll call def trace paths. This I'll make it take the moves, and also I'm going to make this is actually going to be a recursive method. Turns out, so it's going to have a moves, which is the list of moves, yeah, list of moves at each cell. So it's really a 3D array, right? IJ, or that's the current cell I'm visiting. And then S, this is actually going to be a stack holding all of the cells I've visited so far. So a stack is a really nice data structure to use for this, and we'll see it as I fill this in. But let's just think recursively about what I need to do. So what I'll do is I'll just say right at the beginning, okay, I'm visiting this new cell. Let me actually push the location to the stack. So I'll say s.push ij. So again, I'm using the stack thing. Here's the API. I can push, pop, peek, get entire stack, or get the length. Okay. So first thing I'll do is push it. Then what I'll do is I'll look through all the moves. I'm going to look through all possible moves that I'm able to make in the optimal scenario. So I'll say, okay, if move is 1, then I need to recursively visit ij minus 1. I'm supposed to move to the left, right? Okay. Say else if move is 2, then I'm supposed to trace up. Okay, then I need to go up. Else if move is 3, whoops, then I will trace diagonally. All right, so this is all well and good, and actually what I'll say is when I'm done, I will pop this off. Because the idea is what we can do, recursion is really good when you need to branch out in some decisions. So I'm actually not sure which path I'm going to visit. I need to visit them all. So let me first branch out in this direction. Let me say that at this cell ij, I chose to go up, if that was one of my options. Or sorry, to the left, if that was one of my options. Let's say that I chose to go up, if that was one of my options. Let me see what happens there. Then I'll recursively call that, push that element on, and do the same thing. When I'm done exploring that branch, I pop it off, and I can try another one. So that's how the recursion works here. So this is the basic idea. Now what's the base case though? Because this is going to go forever, right? Well, pause the video real quick, see if you think, what's the base case? When do I stop the recursion? So if I look at this picture down here, well, I should stop going once I reach the top left cell, right? And at that point, I can print out what's in the stack, because that will give me what the path was that I happen to enumerate in that particular sequence of recursive calls. So what I will do is make a base case. I'll say if I is 0 and j is 0, that's my base case. I will just print out, there was this method I had, which was get entire stack. I'll just print out what I got. Otherwise, I'll do the recursion, because I'm not done yet. I might still have to branch out and do things. Okay, so fingers crossed. Let's see, did this work? Well, okay, so I have to call it also. Once I've filled in my moves list, I have to call this here. So I'll say trace moves, and I start at index m, index n. And my stack, I just start with an empty stack. Okay, let's see if this worked. So let's see. It didn't like that. For move and moves ij, list indices must be introduced. Oh, you know what I did? I did the NumPy thing, because I'm so used to NumPy. Okay, that's the error you'll get if you do that on a list that's not a NumPy array. There we go. Okay, so it doesn't like self. Let's see, where's self? Oh, well, this isn't actually part of an object, so I don't need self. This was just a global method. Okay, did I get it? Did I get it? Yes, I believe I did. Okay, so remember, we agreed in class that there were 3 possible solutions here. They all if I'm tracing from the back to the beginning, they all start off the same. So 6, 5, 6, 4, 5, 3, 4, 2, 3, 1. And here's where the branching occurs. So what's different? Well, the first branch I go down is 2, 1. And then there's another branch, and there I go to 1, 1. And then I'm done. But if I back this up 1, I'm still at 2, 1, right? So this is where the recursion backs up, pops off the stack. Now I go to 1, 0, and that's the second option here. You see that? Okay, now I pop this back off. Actually, there are no more options, so I pop this back off. I come back up here, and actually go, now I'm back at 3, 1. Now I visit 2, 0, which you see there, and I only have one option, which is to go to 1, 0. So it's a pretty neat little algorithm. Okay, so I haven't decided yet. Am I going to give you an exercise on this where you print things out nice or not? So it'll be a surprise for you whether or not there is an exercise on the next page. Okay. Oh, actually, let's do one more example real quick, just to make sure that this holds water on not just one example. So let's look at it on topology and topography. And I love this example because I work in an area called topology, which people always think is topography. In some contexts, I guess there is a slight overlap between topography and topology, but topology is much more general. Okay. But I like that example. So let me load that one. Okay, so this is what we get. First, before we run the code, let's count how many paths are there. This one is a little more complicated, which isn't surprising because it's longer. Because I branch here, let me remember, I'm going in this branch. Okay, this branches out in 2 ways. Let me go this one. And then this branches out in 2 ways. Let me go this one. Okay, so that's one path there. If I back up, I get 2 paths there. If I back up, I actually get 2 more paths there. If I back up, I get 2 more paths. So if I count it right, let's see, it should be 2, 4, 6, 7, I think. 7 paths. So let's see if I'm right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, more than 7 paths. Well, let's see what they look like. Well, one thing you notice right away is that they all pretty much agree towards the end. And that makes sense. That matches this picture. The branching doesn't occur until the middle because they agree on topo. Okay. So 1, 1, 2, 2, 3, 3, 4, 4, that makes sense. Those would all be in the optimal path. It would not behoove you to remove or add any characters in the first 4. Okay, let's see the other ones. Let me count the branches more carefully. Clearly I missed. So I can see here that, okay, this one branches into... Oh, okay, yeah, I missed some of the branches down here. Okay, but so there are 10 total. So 8, 10, 7, 9. They're all going to start with that. But one of them goes to 7, 8, which is here. Okay, so actually the 4 of them branch off from here. Is that right? So I can see that's one branch, and then this is 2, 3, 4. Okay, yeah, I see the 2. I forgot to count those branches coming this way. Okay. All right, this all matches up here. So cool, look, I didn't even have to work that hard. The recursion just did it for me. So there, basically once you get past, what this is telling us in a nutshell is once you get past topo, there's a bunch of things you can do because none of these really match. Except for the Y. Okay, yeah, so this, basically you can do a bunch with the LOG and the graph. Yeah. You can do a lot with log and graph. There's a lot of ways to make those match to each other. That's where the dominant cost occurs. I guess it's not really surprising that the cost would be 5 because, one thing you can do is just remove all these. GRAPH. Or I guess, match the first 3 and then remove the last 2. You can see that's one way of doing it. All right, so I just wanted to show another example. And that's it for now.